Hey, how's it going there? Cool. We got some people here. Not hundreds, but people. That's good. All right, let me get this thing adjusted. All right. Okay. Hi. There we go. Morning. Okay, cool. Let me get this adjusted so it's looking pretty good. Okay. So I hope you all had a good weekend. Well, maybe we should wait a second. Let me see how many people we have. We got 3. That's more than 1 and less than 7. Either way, we will do this, even if we only have a few people. And but I think I'll wait maybe 1 or 2 minutes just to see how things go. It's 11:02, and then we'll get started. Um, that probably sounds like a pretty good idea. But everybody doing okay? The sun is shining. It's beautiful. Cool. Okay. All righty. Well, 11:03. We'll give it a start and see how it goes. Um, uh, I'm really geeked out about this subject, astronomy. This actually was my research area in grad school, astrophysics, and I hope you can get some feeling for that excitement through YouTube. I hope. Today, I wanted to talk to you guys about stars. And I think we're all interested in stars, I would hope, not just because you guys are here, but because humans, I think, are naturally excited about stars because they're so cool to look at night and you see them. And I'm going to talk to you to start about some of the brightest stars that we can see. Okay. And I wanted to start that conversation with serious, and not just because it's inviting so many fun puns regarding "Are you serious?" Okay, so anyway, when you look up brightest stars in the sky, you'll get lists, and number one is Sirius. Yes, I am serious. Okay, so here's of course the trick. When you look up this list of number one, number two, number three, and so on, and there's Rigel on there, Arcturus, and then so on and so on. This is actually a bit of a trick, isn't it? Because when we're talking about the brightest stars that we can see, is Sirius really the brightest star that we can see? You answer in the chat. Relative? Oh, I see what you're saying. Nice try. We're going to get to that later, guys. The idea of how absolutely bright they are, but I did mean how bright they are in the sky. Is Sirius the brightest star in the sky? Yes or no? Cool. I think I got you. I think your voice analysis already indicates to you that I'd like you to say no. Sirius is not the bright. Oh, see. Oh, cool. All right. So, But why is it not the brightest star in the sky, even though it's listed? Oh, yeah, that's wrong too, Hannah, but good point. There is actually a way brighter star visible to us. Which one is that? Ironic. Yes, exactly. Ironically, it was mentioned earlier by Carly. The sun is a star. Okay, and people kind of tend to forget that because we think about the sun being like the sun, and then there are stars, right? And they're different things. Well, they're not. Our sun is a star. Okay, so before we start talking about Sirius and Rigel and Arcturus and all that stuff, we want to kind of lay a baseline of understanding a little bit about our sun, at least about some basic facts. So Sirius is not the number one in the sky. It is the number one in the night sky. And if you carefully look at those lists they give you, if they're put together carefully enough, then they will say, what are the 10 brightest stars in the night sky? That's an important distinction. So we'll stick with the number one here with the little asterisk in the night sky, because of course the sun is not in the night sky. Well, what about white nights in the Arctic? Okay, so yeah, so we mean when it's dark, okay? So when it's dark outside, when the sun is blocked by the earth, we can't see it, then Sirius is the brightest star in the night sky. So let's talk about our sun to get a baseline, actually, first of all, to get an idea of how these other stars compare to our sun. Okay, so you guys have probably learned a few things about our sun before, and we just first of all want to kind of think about what information is even useful or what we want to know about something like the sun or any other star. So what are the things you guys are think we could measure as scientists? Just throw some stuff in the live chat. What do you think we could measure and find out, and how we could classify stars? Just write it in the live chat. What are some properties we can write down about the sun? Okay. So, cool. So luminosity. So, I'm gonna. Okay. Cool. I'm gonna actually take brightness as a separate one. Okay. Cool. I think those are the main ones as well. I agree with you guys. If we come up with a few other ones, we'll come back to those in a minute. But let's just gather up some facts for a second. Now, one of the classic things here is that all the numbers are really, really large. Okay, so when we look, for example, at the mass of the sun, which you just say like this, we write it like this. We put a little M with a little circle with a dot in it as a symbol for our sun. That mass is just super big. Okay, it is 2 times 10 to the 30 kilograms, which is like redonkulously large. So we have really a very, very hard time understanding that in terms of an absolute number. And I talked to you guys about how difficult big numbers are to understand. So we tend to actually rewrite these masses differently. Okay, so one step would be to compare it with something that's maybe a little bit easier to grasp, like the mass of the Earth. And you're like, sure, that's really heavy too. So maybe that's not the best, but at least we can get an idea there. We can say, okay, this is about 330,000 Earth masses. And for the Earth, we just put a little cross in the middle. So 330,000 Earth masses. Okay, but that's also super difficult to understand. So actually what we'll do is we'll actually reference everything in terms of our sun. So this is a little bit making this into a trick question like, well, how heavy is the sun? What is the mass of the sun? And you can just be like, well, I know that. It's one solar mass. Okay, so the mass of our sun, we can just say, oh, okay, it's one solar mass. Done. And you've explained it. And now, of course, the reference here being that its mass is 2 times 10 to the 30. But now that we've defined this as kind of a reference frame because our sun is our star, then we can always do the same thing with other things, of course. So, for example, luminosity, we can say, of course, the luminosity of the sun is one solar luminosity. And just to explain what that is, luminosity is the total power output of radiation that a star produces. And of course, our sun produces one solar luminosity. Okay, and that's 3.8 times 10 to the 26 watts. Okay, that's a really, 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 really big number. Okay, of course it is. Okay, and you can't even like uh, compare it to anything reasonable. So like all humans on Earth, in terms of our power consumption, probably about 10 to the 9, 10 to the 11, 10 to 11 watts. So the sun puts out as much power in 1 second, as much energy in 1 second as humanity would consume in like, oh my God, a million years, something like that. Okay, so a couple things here. Now, next thing, you guys mentioned temperature. Okay, now that's actually interesting that you should mention temperature because you meant something with that, but it's actually a little bit ambiguous because when you said temperature, the temperature of the sun, you meant the temperature of the sun where? Just type it in the chat. Temperature of the sun where? I think you had a certain thing in mind. Maybe not. You guys still there? Got 3 people here, so I think you're still here. So you're not sure? There's really 2 answers that come to mind. Either one will be fine. Surface, super. Yeah. So I think generally we think about the temperature of the sun at the surface. Okay. And I think you guys realize core, exactly. That's the other one. So you have a variety there. And of course, our expectation is that the sun would be cooler at the surface than it would be at its nucleus, at its core. Okay. And that's true. The surface temperature is quite chilly at about 5,700 degrees Kelvin. Sorry, just 5,700 Kelvin. So, T surface, 5,700 Kelvin. And I say that's pretty chilly because at its core, it's tens of billions of degrees, a million, sorry, 10 of millions specifically, about 16 times 10 to the 6 Kelvin at its core. So its nucleus at its center, the temperature of the sun is about 16 million Kelvin. So that 5,700 at the surface is actually not as hot. Okay, good. So now let's keep going here a little bit on the facts about our sun. Super hot. Obviously, the sun is at its surface relatively cool at 5,700 Kelvin, which is extremely hot. That's why it glows. Okay, so let's keep going here. The radius of the Earth, the radius of the sun. Again, sun is really big. Okay, the sun is really, really big. Okay, hi, Sammy. So the sun is really, really big. Specifically, it is 686,000 kilometers. 686,000 kilometers. Okay, and just as a reference, the radius of the Earth is about 6,700 kilometers. So this number is about 100 times larger than the radius of the Earth. Okay, and of course that means if you imagine a picture of the sun, here's the sun, okay, sun, okay, and then you have the Earth, and the Earth, of course, would be blue. That if you kind of put a dot there, 1, 2, 3, 4, 5, 6, 7. Okay, there are the dots of the Earth going across. You could put 100 Earths next to each other, and it would span the radius, the diameter of the sun. So 100 Earths fit across on the surface of this. It's kind of a good thing to keep in mind, a nice little fact to throw around when you run out of stuff to talk about when you're, chatting with somebody. That's what I do. That's probably why cocktail parties, I end up being pretty lonely. Anyway, so you have 100 Earths next to each other across the surface there, across. And the question I have for you, if that's the case, how many Earths fit inside the sun in terms of the volume? So, okay, we've got those Earths across the surface, but how many Earths actually fit into the sun? Just type the answer in the live chat. So 100 Earths fit across the face of the sun, across next to each other. How many would fill the volume? If you compare the volume of the sun to the volume of the Earth, how many Earths would fit inside the sun? Don't be shy. Type an answer in the live chat. Okay, you guys don't know? How many Earths would fit inside the sun? Is it too easy? Or is it too hard? Or did you fall asleep? Or all of the above? That doesn't make any sense. All right, we'll make it multiple choice. Okay. I'm going to give you 3 answers. 100, 10,000, or 1,000,000. Good, Carly. Good. So 1.3 million. I think you just looked it up or worked it out. So if 100 fit across, right, the face of the Earth, you could basically fit 10,000 Earths on that surface. But of course, it's a volume, so it would be the cube of the radius, because the volume of a sphere, 4/3 pi r cubed, means there's about room for 1,000,000 Earths inside the sun. And you're like thinking, wow, that's really, really, really big. Okay. So, but it shouldn't have been too surprising, because we said 330,000 masses of Earths are the mass of a sun, so of our sun. So that kind of makes sense. Good. So let's keep going here. We got the distance to the Earth. And we're going to pull a little trick here because the distance from Earth to the sun is 149.6 million kilometers. Man, that's really hard to picture. So we're going to do two tricks. Whoop, two tricks. Okay. We're going to say, okay, fine. It's 149.6 million kilometers, but that's really, really useless because that distance we can't picture. It's way too big. So there's two ways you can think about this. And the first thing, we're going to pull the same trick we pulled for the other things, including that we said, what's the luminosity of the sun? We said, well, the luminosity of the sun is one solar luminosity. And what's the mass of the sun? Like, well, the mass of the sun is one solar mass. And we'll do the same thing here, where we're going to say the distance from the sun to the Earth is 1. And we just use that unit. And specifically, the name of that unit that we use is the AU, or the astronomical unit. So by definition, the distance from the sun to the Earth, the mean distance, okay, the semi-major axis of the elliptical orbit of the Earth, okay, is 1 AU, defined as astronomical unit. And that makes other distances much easier to comprehend. So when we talk about the distance to Jupiter, for example, we can say Jupiter is about 5 AUs from the sun. Saturn, 10. Uranus, 20. Neptune, 30. Pluto, 40. Interesting. 5, 10, 20, 30, 40. I can remember that. 5, 10, 20, 30, 40. Okay. 5, Jupiter. 10, Saturn. Uranus, 20. Saturn, Neptune, 30. And then Pluto is at 5, 10, 20, 30, 40 AU. That's a sequence. Okay. But again, we're using a little trick to be able to make the number more reasonable. So we call 1 AU. The other trick we're doing is we're going to measure this distance in light distance. How long would light take to travel the distance to the sun? And I'm assuming you've heard that it's about 8 minutes for light to travel from the Earth. From the sun to the Earth. So we'll call the distance 8 light minutes, or 1 AU. And both those numbers make it a lot easier for us to understand the distances. Okay, let's see. Brightness. We're going to talk about brightness. And what we mean by that, brightness, is kind of, what we mean by that is how bright does something appear, apparent magnitude. How bright in the sky does a star appear? And that's what we mean by brightness versus luminosity. And luminosity would be a measure of absolute magnitude. How bright is it? How much light does it put out? Whereas brightness is kind of the apparent magnitude, how bright something appears in the sky rather than how bright it absolutely is. And we're not going to define that more closely here, but this idea of apparent magnitude compared to absolute magnitude, that's an important concept that we're going to come back to. Okay, so we're about halfway through the class, and we've talked about our sun a little bit, and now we can talk about those other stars and compare them. But there's one important fact that we haven't really discussed yet, which is how to talk about our star in terms of what kind of star it is. Okay, we're going to get back to that, but I'm going to at least just give you the language. And specifically, our star is classified as a type of star. And that's what we're going to get into, because I think, not that that's everything, but our star is a G2 main sequence star. So G2 main sequence star. So that's the name or classification of what kind of star we have, our sun. And we're going to learn a little bit about what these things mean, specifically G2 and then main sequence. Okay, and it'll make more sense when we compare them to the other stars. Okay, I'm going to take a picture of that, and while I'm taking a picture, you guys can give me feedback on whether what we're doing right now is what you were expecting. Is it boring? Is it too fast? Is it too slow? Is it just right? Or don't be polite because I'm doing this for you. Interesting? Okay, good. Okay, good. Okay, let's keep going then. And oh, hey, I'll just give you the list of stars and you pick which one you want to talk about first. So here's the stars I'm going to talk about. Sirius, Arcturus, Rigel, Betelgeuse. There we go. And I think that's the list. Betelgeuse. Okay. Your choice. Oopsie, I didn't even point the camera at it, so it's hard to see. So here are the stars. What do you want to talk about? Betelgeuse? You want to do Betelgeuse? Betelgeuse. Betelgeuse. Okay, cool. So let's start with Betelgeuse, which I think is an excellent choice. I think it's an excellent choice because it's such an extreme contrast to our sun. And we'll get to that and be like, holy crap, this star is bizarre. Okay, so Betelgeuse is in Orion. And specifically, it's called, it's called Alpha Orion. And just to clarify something, when we have a, whoa, is that Alpha showing up? Not really. Okay, so whoop, Alpha Orion. So when you have a constellation, the names of the stars in that constellation are ordered from alpha to whatever Greek letter in order of brightness. And for Orion, it's a bit goofy because Betelgeuse actually varies in brightness quite a bit. So it's sometimes the brightest and sometimes it's not, because sometimes Rigel is brighter, but it's given the label Alpha Orion as well in order to kind of, well, it's got to be one, right? And then Rigel's Beta Orion. So let's get some facts about Betelgeuse. And here we go. So so the distance to Betelgeuse is about 643 light years. That's really, really far. Okay, which is fascinating. It's actually relatively far. It's the furthest star that we have in our group of stars to look at, yet it is extremely bright. Okay, Betelgeuse is extremely bright, and specifically on our list, it's the 10th brightest star in the night sky. Okay, number 10 in the night sky means because it's so far away and it's still number 10 on our list, what can you tell me about Betelgeuse in terms of what it's got to be like if it's still the brightest, even though it's so far away? Still in the top 10 for brightness. Can you tell me about this star? Good. Good. It's big. Good. And big, I think you mean radius, correct? Yep. Yep. Okay. And well, good. No, it's actually not hot, which is fun. It's not hot, but it's big. Okay, it's actually not hot at all. The temperature it has, I'll give you this much. The temperature it has is actually cooler than our star. Our star is 5,700, and its temperature is about 3,590. It is not hot, and because of this temperature, it actually has a different appearance from our star. Our star appears pretty white with a like tendency towards yellow, right? But this star, Betelgeuse, is very red. It's actually red. Okay, so because of the temperature of the stars varies dependent on the temperature. Okay, now you guys have talked about in physics class about the visible spectrum, right? Roy G. Biv. Okay, and casually in our conversational style, we'll sometimes say, "Whoa, that's red hot. That is so hot. It's red hot." But actually, for glowing things, red is actually relatively cool. The reason we call something red hot when it's very, very hot is because when you get something to glow, such as you're cooking your iron that you're smelting or whatever, that's the first color that we see, because as the temperature gets larger and larger, then red, shining in red light, is the first uh, incandescence, self shining that you see. When something gets even hotter, it becomes white hot. And then, strangely enough, actually, blue hot is even hotter than red hot, even though we don't talk about it this way. Now, because for a long time, astronomy has sadly been dominated by men, um, uh, we've really, men having not as much number range sometimes, the color range as women. I'm not sure if that's generally true anymore, but it seems to me that this whole blue, indigo, violet for a lot of men is too complicated. So we talk about this stuff over here as just blue, and this stuff just as red. So when we talk about that range, we will just use those two colors to signify low temperature stars, red stars, and high temperature stars we'll generally consider just blue. Okay, so that's kind of the distinction there, red and blue. So because Betelgeuse is relatively cool, it is a red star. Okay, it's a red star. Okay, now the other thing that Carly said, yes, it's big. It's actually really, really big. And specifically, the radius of this thing is absurdly large. It is about 400 times the radius of our sun. 400 times the radius of our sun. And to be more precise, that's about 617 million kilometers. Okay. Now, this is the part that's going to freak you out. Should freak you out, because this number right here, 617 million kilometers. Well, what does that mean? That means it's about 4 AUs. Okay. And if that doesn't do this to you, woo, then you haven't been paying attention, because 1 AU is the distance from the sun to the earth by definition. So that means Betelgeuse's own radius of just the star is 4 times bigger than the radius of the orbit of the earth around the sun. That means if our sun were as big as Betelgeuse, it would go almost all the way to Jupiter. Okay, all 4 of our inner planets, Mercury, Venus, Earth, Mars, would be consumed by this star because it's so bleeping big. Okay, so it is very, very big, and that's why we classify it as a giant, and specifically, it is a supergiant. Okay, so, and we'll get to what that means. It's a red star, and it's a supergiant. and it's a red supergiant, which is not a red giant. That's important. It's a red supergiant, and it's different from a red giant. We'll get back to red giants later to talk about that. We actually have one on our list, but this is not one, and it's not a red giant. That's important to distinguish. Okay, other facts about Betelgeuse that we should know. Because it's so big, even though it's not very hot, because it's so big, even though it's not very hot, that means it's extremely bright, okay? And specifically, its luminosity is about equal to 100,000 solar masses, which is absurdly large. So our sun, comparing it to Betelgeuse has 100,000 times the luminosity of our sun. Okay, now a couple other facts that are important here. This will explain. Good. It is so bright. Okay, it is so bright because even though it's not very hot, okay, the brightness of an object depends on two factors. Okay, the temperature will affect it, because if you have something that's blue compared to red, or white hot compared to red, then it will be brighter, but only if it has the same area. So if you imagine the Earth is this, and it's white hot, yellow hot, right? But this planet, this star. Good. Hang on a second. We'll get back to Hannah's question. So how do we the star itself is so much bigger that it's basically like a gigantic glowing ball, even though each square area of the surface compared to square area on the surface of the sun produces less light because its surface area is so much bigger. Therefore, it produces way much more light going out, more energy coming off of it, and that's why it can produce 100,000 times the light. The radius, 400 times as big, right, means that it has about 160,000 times the area of our sun, meaning even though each square meter of that surface produces less energy radiating off because hot objects glow, because it has so much more area, it produces so much more light. Good. Hannah asked, how do we measure these things? That's a really good question. So obviously we have to look at these stars with telescopes. Okay, and when we look at the telescopes, we can measure certain things about the star. Okay, and specifically things we can measure is first of all the light in terms of its color, right? Because is it red, or is it blue, or is it white? And we can measure that more precisely. Okay, because you can narrow it down to specifically what color it is. Okay, so when we measure that, okay, so color, okay, so the color we measure is really the peak frequency, okay, and the frequency of the light where the star shines the most can tell us the temperature, because cool, red, hot, blue, okay? And this color, confusingly, we categorize with one of these letters. Okay? The colors or spectral types are classified with a main letter. Now remember, our star, the sun, is a G2 star. So inside each of these letters, we have then 10 subcategories. where again, confusingly, 0 is the hottest, 9 is the coolest, which is weird. So G2 is actually a pretty relatively hot star in the G category, just moving towards the F. Okay, now these letters here are confusing. Okay, and they're still used because astronomy is probably the oldest science there is. Is that true? I think that's true. Okay, because it's been around so long, people have been looking at stars and people have been classifying stars and all those things. It's important for navigation for ships, etc. So that's why it's such an old science. And we continue to use old ways of looking at things, even though they're kind of out of date. So last thing I'm going to, maybe second to last thing, I'm going to teach you a way to remember these letters because there's a mnemonic device associated with that. And it's maybe a little bit out of date would be one way of looking at it. Sexual harassing is maybe too strong, but it's a little bit okay. Anyway, I'll let you know what it is. And so no means no. Don't make people kiss you if they don't want to. Okay, but here's the thing: how astronomers have been remembering this, and if I know a better mnemonic device, I teach it for you. But O, B, A, fine, girl or guy, pick your poison there, kiss me, is the way to remember those letters, O, B, A, F, G, K, M, okay? O, B, A, F, G, K, M, where O is the hottest and M is the coolest type of star, okay? So this is how you can remember that. And if you come up with a better mnemonic device that you could help the astronomy community with, that'd be great. But this is the one I think that people still teach. That would be good. Okay, so we have color as one thing we can measure. Okay, now the other thing we can measure is apparent brightness. Okay, so how bright does it appear to us? Okay, so we can measure how much light comes to us from the star. Okay, and that's just using a telescope. Okay, I think that makes sense. You can just collect how much light comes, and we say, okay, per second, yada yada, we get that much photons, so much light is hitting us from that star. That'd be the second category there that we can measure. And a third category that I'm going to mention right now, which is the main measurement, is for stars, we can also measure their distance. And distance, the most straightforward way of measuring distance tends to be parallax. Okay, and just to explain what parallax means to you guys in a simplistic way, we use parallax with our two eyes. So if you hold a finger in front of you and you then open one eye and look at it, and then look at it with the other eye open, just one open at a time, you'll see your finger popping back and forth. Okay, now if you repeat that experiment and hold your finger further away, yeah, and you'll do that again, you'll notice that the finger pops back and forth less. The amount of shift back and forth, the parallax shift that occurs when you're looking at an object from two different locations, depends on the distance. Okay, and we can do the same thing with stars. And to make that work well, we have to measure the parallax of that star, how far it shifts in the sky based on its being observed from two different locations, that are as far apart for us as possible. So what we do there is we wait half a year and measure it from one side of the sun to the other side of the month. Well, then our two eyes are basically 300 million kilometers apart, and then the star shifts back and forth quite a bit. And if it shifts 1 arc second, 1/3600th of a degree, then it is 1 parsec away. That's where the word parsec comes from. So 1 parsec means 1 arc second of parallax. Okay, good. It is 11:45, and I'm going to stop there because that's how long I said I'd go. And I'm planning on doing this again on Wednesday. So thanks for coming, guys. I hope you come back on Wednesday to learn more about stars and how we measure things about them and all that. Bye-bye. Okay, try again. Beenden. Here we go.